What if I told you some of the most mysterious objects in our universe might not be what we've always assumed? Black holes, those cosmic vacuum cleaners born from collapsing stars, could have a far stranger origin story. Picture this: tiny, ancient black holes, smaller than an atom yet heavier than a mountain, forming in the first chaotic moments after the Big Bang. These aren't the black holes we've seen tearing stars apart or lurking at the centers of galaxies. These are primordial black holes, and they've been hiding in plain sight for over 13 billion years. Think about what that means for a second. If these elusive objects exist, they could be the invisible architects of the cosmos, the missing pieces behind dark matter, the unseen hands shaping the first galaxies, even the reason our universe looks the way it does today. It's a radical idea, one that turns textbook astrophysics on its head, because if primordial black holes are real, then everything we thought we knew about the universe's infancy might need rewriting. That's the journey we're starting today. We'll venture into the wild frontiers of cosmology, where scientists are chasing clues that could upend our understanding of reality itself. From ghostly gravitational whispers to the explosive dawn of time, we'll uncover how these primordial relics might solve puzzles that have baffled astronomers for generations. So if you've ever looked up at the night sky and wondered what secrets it's keeping, you're in the right place, because the universe's greatest story might be hiding in the smallest, darkest corners of space, and we're just beginning to learn how to listen. The idea of primordial black holes didn't come out of thin air. It was born from one of the greatest scientific minds of our time. In the early 1970s, Stephen Hawking and physicist Bernard Carr peered back into the universe's earliest moments and asked a revolutionary question: what if black holes weren't just the remains of dead stars, but relics of creation itself? They realized that in the searing heat of the Big Bang, tiny pockets of space could have collapsed under their own gravity, forming black holes before the first stars even flickered to life. These wouldn't be like the black holes we know today. Imagine a black hole so small it could fit inside an atom, yet packing the mass of an entire mountain. Or one as vast as a solar system, born from a cosmic hiccup in the first second of time. The sheer range of possible sizes makes primordial black holes unlike anything in modern astrophysics. And here's where it gets even wilder, because they formed in that primordial chaos. They could be lurking everywhere, invisible yet shaping the universe in ways we're only starting to grasp. This theory didn't just challenge the textbook version of black holes, it turned the whole cosmic story upside down. If primordial black holes exist, they might be the missing key to some of astronomy's biggest mysteries. Take dark matter, for example, that mysterious substance making up most of the universe's mass. Scientists have spent decades searching for exotic particles to explain it, but what if the answer was hiding in these ancient gravitational traps all along? Or consider the supermassive black holes at the hearts of galaxies, some so enormous they shouldn't have had time to grow so big so fast, unless, of course, they were never born from stars at all, but from the raw energy of the Big Bang itself. The beauty of Hawking and Carr's idea is how elegantly it ties together puzzles that once seemed unrelated, yet for decades, primordial black holes remained on the fringe of cosmology, too radical, too untestable to take seriously. But science has a way of circling back to brilliant ideas when the time is right. Today, with cutting-edge telescopes and gravitational wave detectors, we're finally hunting for these ghostly remnants of the universe's birth. And if we find them, it won't just confirm a bold theory, it'll rewrite the first chapter of cosmic history. To understand how primordial black holes could form in the early universe, we need to rewind time to its most extreme conditions, the very first moments after the Big Bang. Picture a universe so hot and dense that matter and energy were indistinguishable, a seething ocean of particles where gravity hadn't yet settled into the familiar force we know today. In this primordial chaos, tiny irregularities, quantum fluctuations rippled through space like waves on a turbulent sea. Most of these fluctuations smoothed out as the universe expanded, but some regions held onto their extra density, packing so much mass into such a small space that they collapsed under their own gravity. No stars required, no supernovae, just raw cosmic pressure forging black holes from the fabric of spacetime itself. The process might sound simple, but the physics behind it is anything but. Imagine a cosmic pressure cooker where the rules of quantum mechanics and general relativity collide. Inflation, that brief period of exponential expansion in the universe's first fraction of a second, could have stretched these dense regions until they crossed a critical threshold, pinching off into black holes like bubbles separating from boiling water. Or perhaps phase transitions, cosmic rearrangements of fundamental forces, created pockets of space so unstable they crumpled into gravitational knots. The result, black holes spanning an astonishing range of sizes, from ones lighter than a paperclip to monsters rivaling the mass of entire star clusters. What's truly mind-bending is how differently these primordial black holes would behave compared to their stellar-born cousins. Without the constraints of stellar evolution, they could exist at virtually any size, from microscopic specks to colossal giants. Some might have evaporated over billions of years, thanks to Hawking radiation, while others could have grown by devouring surrounding matter or merging with one another. And because they formed before the first atoms, before the first light, they'd carry no telltale signs of stellar ancestry, no orbiting companion stars, no glowing accretion disks. Just pure, unadorned gravity, weaving itself into the cosmic tapestry before the universe even knew what a star was. This raises a thrilling possibility. What if these ancient black holes aren't just rare oddities, but ubiquitous? What if the universe is filled with them, drifting unseen through galaxies, weaving between stars, even passing through our solar system without us noticing? It's a humbling thought that the cosmos might be threaded with invisible fossils from its birth, each one a silent witness to the turbulence of creation. And if we could find just one, it wouldn't just confirm a theory, it would open a window into a time before time, letting us glimpse the universe in its rawest, most explosive infancy. Dark matter has been the universe's most stubborn secret, an invisible force sculpting galaxies, bending light, and refusing to reveal its true nature. For over half a century, physicists have chased shadows, building detectors deep underground, scanning the skies for elusive particles that never appear. But what if we've been searching in the wrong direction entirely? What if dark matter isn't some exotic, undiscovered particle, but something far stranger, primordial black holes, lurking unseen since the dawn of time? The numbers tell a compelling story. When astronomers measure how galaxies rotate, they find stars whirling so fast that the visible matter alone couldn't possibly hold them together. Something invisible must be anchoring them with gravity, something that doesn't emit light, doesn't collide with stars, and doesn't interact with anything except through its relentless pull. Traditional dark matter candidates, like weakly interacting massive particles or Axions, have never been caught despite decades of hunting, but primordial black holes, especially those with masses comparable to asteroids, fit the profile perfectly. They drift through galaxies like silent ghosts, their gravity tugging on stars exactly the way dark matter does, without requiring any new physics beyond Einstein's equations. Here's where it gets even more intriguing. Unlike hypothetical particles, primordial black holes have a built-in advantage. We already know black holes exist. We've detected their gravitational waves, photographed their shadows, and mapped their effects on surrounding space. The leap isn't inventing a whole new class of matter, it's realizing that black holes might have been hiding in plain sight, masquerading as dark matter all along. And the most tantalizing clue, The universe seems to have just the right number of them. Simulations show that if even a tiny fraction of the early universe's energy condensed into primordial black holes, say, 1 in every 1,000 parts, it would neatly account for all the missing mass we've been struggling to explain. But the theory isn't without its challenges. If primordial black holes are everywhere, why haven't we seen more direct evidence? The answer might lie in their size. Asteroid mass black holes, each weighing as much as a mountain but no larger than a molecule, would be nearly impossible to spot individually. They wouldn't shred stars like their supermassive cousins or emit detectable radiation. Instead, they'd weave through the cosmos like invisible threads, revealing themselves only through subtle gravitational fingerprints, lensing distant starlight, nudging celestial objects off course, or perhaps even occasionally colliding to send ripples through spacetime itself. That last possibility opens another fascinating door. When the LIGO Observatory detected gravitational waves from merging black holes, some of the colliding objects were curiously heavy, too massive to have formed from ordinary stellar collapse. Could these have been primordial black holes, meeting in the darkness after billions of years adrift? It's a tantalizing hint, one that's driving astronomers to scour gravitational wave data for more of these unexpected mergers. Every unexplained ripple could be a breadcrumb leading us closer to solving two cosmic mysteries at once: dark matter's identity and the origin of black holes themselves. The stakes couldn't be higher. If primordial black holes really are the dark matter we've been seeking, it would rewrite not just astrophysics textbooks but our entire understanding of the universe's architecture. Suddenly, the invisible scaffolding holding galaxies together isn't an enigma, it's a population of ancient gravitational relics, forged in the Big Bang's first moments. And the best part, we might not need fancy new detectors to find them. The tools we already have: gravitational wave observatories, microlensing surveys, even precise measurements of the cosmic microwave background could soon catch these cosmic ghosts in the act. After decades of dead ends, the answer to dark matter might not lie in the unknown, but in the overlooked. Gravitational waves are like cosmic messages written in the fabric of spacetime itself, and some of them might be carrying secrets from the universe's earliest moments. When the LIGO Observatory first detected these ripples back in 2015, it confirmed Einstein's century-old prediction and opened a brand new way to study black holes. Most of the collisions we've observed so far fit neatly into the expected range for stellar mass black holes, the kind born from dying stars, but a handful of signals have defied explanation, with masses too large or too oddly paired to match our models. That's where primordial black holes enter the scene. Imagine two ancient black holes, forged in the Big Bang's chaos, finally spiraling together after billions of years adrift in the cosmic dark. Their collision wouldn't just send gravitational waves racing across the universe, it would broadcast a fingerprint of their primordial origins. What makes these mergers so special isn't just their mass, but their story. Stellar black holes follow predictable rules. They are born from stars, so their sizes reflect the limits of stellar physics, but primordial black holes, they could be almost any size, from lighter than a bowling ball to heavier than 1,000 suns. If LIGO catches a pair merging with masses that don't fit the stellar playbook, like two oddly matched black holes, or one far too hefty to form from a single star, it could be our first direct evidence of these ancient relics. Even more telling would be spotting mergers in empty stretches of space, far from the star-rich regions where stellar black holes typically form. A collision in the cosmic boondocks would scream primordial, like finding a cave painting in the middle of a desert. The real game-changer, though, lies in the next generation of detectors. Projects like the Einstein Telescope and the space-based LISA Observatory will listen for gravitational waves with unprecedented sensitivity, tuning into frequencies that could reveal mergers from the universe's first billion years. That's when primordial black holes would have been most active. colliding in a youthful cosmos far denser than today. If these detectors catch a chorus of mergers from that era, with masses all over the map, it wouldn't just confirm primordial black holes, it would paint a vivid picture of the universe's wild, formative years. But here's the twist: even silence could be telling. If we scan the early universe and find fewer mergers than expected, it might mean primordial black holes evaporated long ago, thanks to Hawking radiation. Or perhaps they avoided collisions, drifting apart as the cosmos expanded. Every ripple, every gap in the data, is a clue waiting to be decoded, and with each new detection, we're not just studying black holes, we're piecing together a cosmic origin story written in gravity itself, one collision at a time. Detecting something invisible might sound impossible, but astronomers have a brilliant trick up their sleeves, watching how these hidden objects bend the very fabric of reality around them. When a primordial black hole drifts between us and a distant star, its gravity acts like a cosmic magnifying glass, warping spacetime just enough to distort the star's light. For a brief moment, the star brightens in a telltale curve before fading back to normal, leaving behind a gravitational signature with no visible cause. That's microlensing in action, and it's become one of our most powerful tools for hunting these ancient shadows. Projects like the Optical Gravitational Lensing Experiment and the Gaia Space Telescope have turned the entire Milky Way into a detective's playground, scanning millions of stars for these elusive flashes. Some of the events they've captured defy easy explanation: sudden brightenings with no visible lensing object, or distortions that move too fast for ordinary stars. Could these be primordial black holes, some as small as asteroids, silently crossing our line of sight? The math is tantalizing. If just 1% of dark matter consisted of these objects, microlensing surveys should have already spotted hundreds of them. Yet the signals we've found are strangely sparse, hinting that primordial black holes might cluster in ways we don't yet understand, or that they're hiding in mass ranges we've yet to probe. The real magic happens when you combine microlensing with other cosmic clues. Take the mysterious flares from stars that brighten and dim in ways no known companion can explain. Some researchers suggest these could be stars orbited by unseen primordial black holes, their gravity tugging asymmetrically on stellar plasma to create bizarre, unpredictable flickers. Or consider the way entire star clusters sometimes move slightly off-kilter, as if tugged by invisible anchors scattered through their midst. Each of these anomalies could be a breadcrumb leading us closer to mapping the hidden population of black holes woven through our galaxy. But microlensing isn't just about spotting individual black holes, it's about reconstructing their cosmic history. The duration of a lensing event reveals the object's mass, the direction and speed hint at its trajectory through the Milky Way. Piecing together enough of these events could let us trace where primordial black holes congregate, whether they lurk in dark matter halos, spiral arms, or even our solar system's backyard. And here's the kicker: some models suggest these objects could be whizzing past us right now at hundreds of kilometers per second, too small and dark to notice until they momentarily magnify a star halfway across the galaxy. The challenge is separating true primordial black hole signals from cosmic imposters. Dwarf stars, rogue planets, even dense clouds of dust can mimic microlensing events. That's why next-generation telescopes like the Vera Rubin Observatory are game-changers with their ability to scan the entire visible sky every few nights. They'll catch lensing events in unprecedented detail, filtering out false alarms with statistical precision. If primordial black holes are out there, this flood of new data could finally corner them, transforming ghostly anomalies into a detailed census of the universe's oldest gravitational fossils. What's at stake isn't just confirming a theory, it's rewriting our understanding of the cosmic dark. Every unexplained flicker of starlight could be a message from the Big Bang's first seconds, a whisper from an era before atoms or light. And if microlensing reveals these black holes are indeed woven through the galaxy's fabric, it would mean we're living in a universe teeming with ancient gravitational relics, each one a silent witness to the chaos of creation. The stars we see at night might be just the visible tip of a far stranger cosmos, where darkness holds secrets older than time itself. The universe wasn't always a tapestry of glittering galaxies and vast cosmic webs. It began as a nearly smooth sea of matter, almost featureless. So how did we get from that primordial simplicity to the intricate structure we see today? The answer might lie in those tiny gravitational traps we've been chasing: primordial black holes. Think of them as cosmic anchors scattered through the early universe, each one a knot in spacetime strong enough to pull surrounding matter into its grasp. While ordinary matter was busy being pushed apart by radiation pressure in the universe's first few 100,000 years, these black holes would have been immune, their gravity quietly gathering gas and dark matter into dense pockets. Over eons, those pockets could have grown into the first stars, the first galaxies, the very foundations of everything we see. Here's why that's revolutionary. Normally, gravity needs a head start to build cosmic structure. Tiny quantum fluctuations from inflation that were stretched across the universe, creating slightly denser regions where matter could eventually collect. But that process takes time, and observations show some galaxies formed astonishingly early, their light reaching us from just a few 100 million years after the Big Bang. That's like finding a skyscraper in the middle of a desert where only tents should exist. Primordial black holes could solve this puzzle by providing ready-made gravitational wells, jump-starting galaxy formation before the standard model says it should have been possible. Imagine tossing boulders into a still pond. The ripples they create would organize the water's movement far faster than random waves ever could. The numbers back up this wild idea. Simulations reveal that even a sparse population of primordial black holes, just one for every few thousand cubic light years, could have drastically reshaped the early cosmos. Their gravity would have created overdensities, regions where matter clustered more tightly, long before ordinary density fluctuations had a chance to grow. These hotspots would have acted like cosmic magnets, funneling gas into their grasp and igniting the first stars in a fraction of the usual time. And because black holes don't just disappear, their influence would have persisted, weaving themselves into the fabric of galaxies as they formed. Some might even linger today, lurking in galactic halos or anchored at the hearts of star clusters, invisible architects of the structures they helped create. But the real marvel is how elegantly this ties into the universe's largest scale patterns, the cosmic web, that sprawling network of filaments and voids connecting galaxies across billions of light years, mirrors the distribution of density fluctuations in the early universe. If primordial black holes were unevenly distributed, their clustering could have imprinted that same web-like structure onto matter, like invisible hands molding the cosmos into shape. Recent observations of unexpectedly massive black holes in the distant universe add fuel to this fire. These behemoths, weighing billions of suns, appear fully formed when the cosmos was less than a tenth of its current age, far too soon to have grown from stellar seeds alone. Unless, of course, they started as primordial giants, planted like cosmic keystones in the universe's infancy. Yet mysteries remain. If primordial black holes played such a pivotal role, why don't we see more obvious signs of their influence? The answer may lie in their subtlety. Unlike stars or gas clouds, they wouldn't leave bright trails as they shaped the cosmos, just gravitational fingerprints on the motions of matter. Future telescopes mapping the universe's large-scale structure in unprecedented detail could finally spot these imprints, revealing whether the cosmic web's threads were spun by the gravity of invisible black holes. And if they were, it would mean these ancient relics didn't just witness the birth of galaxies, they midwifed them, sculpting the universe's grand design from the shadows. Stephen Hawking's most startling revelation about black holes wasn't their power, it was their fragility. He showed that these cosmic titans don't last forever. Through a bizarre quantum quirk at their boundaries, they slowly leak energy, shrinking over unimaginable timescales until they vanish in a final, fiery puff of radiation. For primordial black holes, this isn't just theoretical, it's existential. If the universe forged countless microscopic black holes in its first moments, Hawking's math says most should have evaporated by now, their deaths lighting up the cosmos like firecrackers in the dark. Yet our detectors remain silent, so where's the fireworks show? This contradiction lies at the heart of one of cosmology's most tantalizing puzzles. The paradox hinges on size. A black hole with the mass of a small asteroid would take about the current age of the universe to evaporate, meaning the tiniest primordial black holes, those lighter than 1 billion tons, should have already met their explosive end. We'd expect to see their final moments as bursts of gamma rays or strange radio signals, especially in regions where dark matter is thought to cluster. But despite decades of searching, from orbiting gamma-ray telescopes to ultra-sensitive radio arrays, the sky shows no evidence of these dying screams. It's as if entire generations of black holes vanished without a trace. This leaves scientists with two equally intriguing possibilities. First, maybe primordial black holes weren't as small as we imagined. If most formed with masses greater than a small moon, say, a quadrillion tons, they'd still be evaporating today, their Hawking radiation too faint for current instruments to catch. That would make them cosmic tortoises rather than hares, aging so slowly they've barely begun their lifespan. Alternatively, perhaps the earliest universe didn't produce black holes in the quantities we've assumed. Inflation's density fluctuations might have been smoother, creating far fewer gravitational collapse points than early theorists calculated. Either scenario reshapes how we view these objects, not as fleeting quantum specters, but as enduring gravitational landmarks. There's a third, even wilder option. Hawking radiation might not work exactly as predicted. The theory relies on quantum mechanics and general relativity intersecting in ways we've never directly tested. What if some unknown physics alters the evaporation process, stretching black hole lifetimes far beyond our estimates? Or what if primordial black holes grow as they evaporate, feeding on mysterious energy fields we've yet to discover? These ideas push the boundaries of known physics, but that's precisely what makes them so compelling. After all, the early universe was a laboratory for extremes, where matter behaved in ways we can barely replicate even in theory. The stakes go beyond academic curiosity. If primordial black holes are evaporating slower than expected, or not at all, it means they could be far more abundant today, lurking in galactic halos or drifting between stars. Suddenly, their potential role in dark matter and galaxy formation becomes even more significant. Conversely, if they truly are rare or short-lived, it forces us to reconsider alternative explanations for cosmic structure and those puzzlingly massive black holes in the early universe. Every unobserved gamma-ray burst, every quiet patch of sky, is a clue waiting to be deciphered. Upcoming experiments might finally break the deadlock. Next-generation gravitational wave detectors could spot mergers between black holes too small to form from stars, direct evidence of primordial survivors. Space telescopes tuned to high-energy radiation might catch the faint death throes of evaporating black holes we've previously missed. Even tabletop quantum experiments, probing the nature of Hawking radiation in simulated black hole analogs, could reveal whether our assumptions about evaporation rates hold water. What makes this paradox so beautiful is how it ties the infinitesimally small to the cosmically vast. Quantum fluctuations at black hole event horizons could determine whether these objects still shape our universe today, or whether they're ghosts of a past we've barely begun to understand. Solving it won't just tell us about primordial black holes, It'll test our deepest theories of how reality works at its most fundamental level, and that's the hallmark of great science, when a single mystery becomes a window into everything we don't yet know. At the heart of nearly every galaxy lies a monster, a supermassive black hole with gravity so strong it bends the rules of cosmic growth. Take the one in our Milky Way, Sagittarius, a star 4 million times heavier than our Sun, yet tiny compared to others like Ton 618, which weighs as much as 66 billion suns. These colossal objects shouldn't exist, at least not by conventional astrophysics. Even if they started as stellar black holes, there hasn't been enough time since the Big Bang for them to gorge on enough matter to reach such staggering sizes. Unless, of course, they didn't start small at all. This is where primordial black holes throw conventional wisdom out the window. Imagine a handful of these ancient relics born already massive, thousands or even millions of times heavier than our Sun, scattered across the infant universe like gravitational seeds. While ordinary black holes had to grow painstakingly slow by swallowing gas and stars, these primordial giants would have had a head start, their immense gravity pulling and surrounding matter at breakneck speeds. Over billions of years, they could have merged with other massive primordial black holes or spiraled into galactic centers, becoming the gravitational anchors around which entire galaxies formed. The math behind this idea is startlingly elegant. Simulations show that just one primordial black hole per early galaxy cluster, each weighing around 10,000 solar masses, could explain the supermassive beasts we see today. These heavyweights would have sunk into the densest regions of dark matter halos, their gravity creating a feedback loop. The more matter they pulled in, the stronger their grip became, accelerating their growth exponentially. By the time the first stars flickered to life, these black holes could have already been well on their way to becoming the cosmic titans we observe, but the most compelling evidence comes from the edges of the observable universe. Astronomers have spotted fully formed supermassive black holes in galaxies so distant, their light has traveled nearly 13 billion years to reach us, meaning they existed when the cosmos was less than a billion years old. That's like finding a skyscraper in the middle of a construction site where only tents should stand. Stellar black holes simply couldn't have grown that big that fast under normal circumstances. But if they started as primordial heavyweights, their early dominance suddenly makes perfect sense. Yet mysteries linger. If primordial black holes seeded these giants, why don't we see more intermediate mass black holes, the missing links between stellar and supermassive varieties? One theory suggests they merged so efficiently in the early universe that few were left behind, or perhaps we're just not looking in the right places, with these middleweight black holes hiding in dwarf galaxies or floating between clusters. Future telescopes like the James Webb Space Telescope could settle the debate by peering deeper into cosmic dawn, searching for the chemical fingerprints of black hole feeding frenzies in the universe's first galaxies. What's truly revolutionary about this idea isn't just solving the supermassive black hole puzzle, it's rewriting the cosmic hierarchy. Instead of galaxies birthing black holes, we might be looking at a universe where black holes sculpted galaxies from the outset, their gravity weaving the tapestry of stars and gas we see today. It turns the standard story on its head. These aren't just occupants of galactic centers, they might be the architects, their invisible hands shaping the cosmos since the very beginning. We've mapped the universe's contents with remarkable precision: dark energy, dark matter, and the tiny slice of ordinary matter that makes up everything we can see. But there's a hitch. Even that familiar matter isn't all where it should be. Astronomers call this the missing baryon problem, and it's like doing a cosmic inventory only to find shelves half empty. The math says there should be more protons and neutrons out there, especially in the vast spaces between galaxies, but our telescopes keep coming up short. The solution might be hiding in the last place we'd think to look: inside primordial black holes. Picture this: trillions of tiny black holes, each no wider than a molecule but heavier than a mountain, scattered across the cosmos like invisible safes. Every atom that falls past their event horizons vanishes from our cosmic accounting, locked away where no telescope can find it. It's not that the missing matter ceased to exist, it's just been stashed in gravitational vaults we've only just learned to suspect. The numbers fit eerily well. If just a fraction of primordial black holes formed with masses between a ton and an asteroid, they could have swallowed enough baryons over billions of years to explain the discrepancy without invoking exotic physics. What's brilliant about this idea is how it turns a problem into a clue. Those missing baryons aren't really lost, they've been hiding in gravitational shadows. When hydrogen gas swirls too close to one of these ancient black holes, it doesn't glow or heat up like it would near a star. Instead, it vanishes silently, leaving no trace except a slight tweak to the black hole's mass. Over cosmic time, this stealthy consumption could have removed enough ordinary matter from circulation to throw off our tallies, and because primordial black holes avoid the flashy drama of their stellar-born cousins, no accretion disks, no X-ray bursts, they've been hoarding baryons right under our noses. The implications ripple across astrophysics. Take the intergalactic medium, that diffuse ocean of gas stretching between galaxies. Its measured density doesn't match predictions, but if primordial black holes pepper these voids, their cumulative appetite could explain the shortfall. Even more intriguing is how this intersects with dark matter. If some primordial black holes fall into the right mass range, they could account for both the universe's invisible mass and its missing baryons, a two-for-one solution that simplifies our cosmic ledger. Critics raise valid questions, of course. If primordial black holes are swallowing baryons, why don't we see more evidence of their feasts? The answer lies in scale. A single asteroid mass black hole might gobble just a few kilograms of matter per century, far too little to notice, but multiply that by trillions of black holes across billions of years, and the numbers add up. Future telescopes could test this by hunting for the faint distortions these objects imprint on the cosmic microwave background, or by catching the rare moments when one passes between us and a distant quasar, briefly warping its light. This isn't just about balancing equations, it's about rethinking where ordinary matter calls home. The universe might be filled with invisible traps, each one a time capsule preserving atoms from the cosmos's earliest epochs. If we're right, then every galaxy, every star, every planet exists against a backdrop of countless gravitational relics, their event horizons holding secrets older than light itself. The missing baryons aren't lost, they've been here all along, woven into the fabric of space in ways we're only beginning to decipher. Black holes have always been the universe's ultimate paradox, places where gravity becomes so intense that even light can't escape, yet where quantum mechanics and relativity collide in ways we still don't understand. But primordial black holes, especially the tiniest ones, might be more than just cosmic oddities. They could be nature's own laboratories, testing the boundaries of physics in ways no particle accelerator ever could. Imagine a black hole so small that quantum fluctuations dominate its behavior, where the fabric of spacetime itself becomes fuzzy and uncertain. These microscopic monsters, if they exist, would be the perfect playground for uncovering the secrets of quantum gravity, the holy grail of modern physics. The challenge has always been bridging two seemingly incompatible worlds. On one hand, you have Einstein's general relativity, which describes gravity as the curvature of spacetime on cosmic scales. On the other, quantum mechanics governs the bizarre behavior of particles at the smallest scales. The problem, they refuse to play nice together. Near a black hole's event horizon, where gravity is extreme and space is pinched to a singularity, both theories break down. That's where primordial black holes come in, because they could span such a wide range of masses, from subatomic to supermassive. They offer a sliding scale of conditions to study. A black hole lighter than a paperclip, for instance, wouldn't just evaporate via Hawking radiation, it would do so explosively, its final moments potentially revealing quantum gravitational effects we've never seen before. Think of it like this: if you wanted to study how water behaves, you wouldn't just look at oceans, you'd examine raindrops, ice crystals, and steam to see how the rules change at different scales. Primordial black holes give us that same versatility for spacetime itself. Some theories suggest that at their cores, these tiny black holes might not even have singularities in the traditional sense. Instead, quantum effects could prevent infinite density, leaving behind a dense, fuzzy ball of energy, a Planck star, or a wormhole to another part of the universe. These aren't just sci-fi fantasies, they're testable predictions that could reshape our understanding of reality. The real breakthrough would come if we could observe Hawking radiation directly. So far, it's never been detected, but a vanishingly small primordial black hole in its death throes might be our best shot. As it evaporates, its radiation would carry signatures of quantum gravity, subtle deviations from what Hawking originally predicted. Some models even suggest these black holes could leave behind exotic particles or dark matter as relics, like cosmic breadcrumbs pointing to new physics. And because primordial black holes formed in the early universe's extreme conditions, they might preserve quantum gravitational imprints from that era, like fossils locked in spacetime. This isn't just theoretical noodling, it's a roadmap for experiments. Next-generation gravitational wave detectors could catch the ripples from microscopic black holes colliding, their unique frequencies hinting at quantum structure. High-energy astrophysical observatories might spot the telltale gamma-ray bursts of evaporating black holes, their energy profiles revealing hidden dimensions or new forces. Even tabletop experiments using ultra-cold atoms or laser arrays are trying to simulate black hole physics, creating analog systems where quantum gravity effects might appear in miniature. The beauty of this idea is its universality. Whether primordial black holes turn out to be abundant or rare, their very existence or absence constrains the possibilities for quantum gravity. If we find them, they'll give us a front-row seat to physics beyond Einstein. If we don't, their absence might force us to rethink inflation, dark matter, or even the nature of spacetime itself. Either way, these ancient gravitational relics aren't just cosmic curiosities, they're keys to unlocking the deepest mysteries of the universe, written into the fabric of reality from the very first moments of time. The cosmic microwave background is like a photograph of the universe's infancy, a snapshot taken when everything was just 380,000 years old. This afterglow of the Big Bang blankets the sky in microwaves, its patterns encoding the seeds of all future structure. But what if hidden in those subtle temperature fluctuations lie fingerprints of something far stranger? Primordial black holes, forming in the universe's first chaotic moments, could have left gravitational graffiti on this ancient light, distortions so faint we're only now learning how to read them. Picture the early universe as a simmering plasma, so dense that light couldn't travel far before scattering off free electrons. When primordial black holes formed in this soup, their gravity would have created tiny ripples, regions where matter clumped slightly more densely around them. As the universe expanded and cooled, these gravitational potholes would have left two kinds of marks on the cosmic microwave background. First, temperature variations, patches of sky where the microwaves appear slightly hotter or cooler because photons climbing out of a black hole's gravity well lost or gained energy along the way. Second, and more telling, distinctive twists in the light's polarization, the orientation of its waves caused by how these gravitational pits scrambled the plasma's motion in their vicinity. The beauty of this idea is its testability. While other dark matter candidates might leave no trace on the cosmic microwave background, primordial black holes, especially those between 10 and 1,000 solar masses, would have warped spacetime enough to produce measurable anomalies. Current telescopes like Planck have already mapped the cosmic microwave background's temperature to exquisite precision, but next-generation instruments like the Simons Observatory and CMBS-4 will examine its polarization with unprecedented detail. They'll be searching for swirling patterns called B modes that no ordinary density fluctuation could create, patterns that might betray the presence of primordial black holes lurking in the universe's first light. Here's where it gets even more fascinating. The cosmic microwave background isn't just a static image, it's a layered record of different cosmic epochs. If primordial black holes were abundant enough, their collective gravity would have subtly altered how sound waves propagated through the early plasma, leaving a unique signature in the spacing of temperature peaks across the sky. Some theorists argue this could explain why certain large-scale features in the cosmic microwave background appear oddly suppressed, as if something, perhaps a population of primordial black holes, was smoothing out fluctuations on those scales. The implications stretch beyond mere detection. If we find these gravitational fingerprints, they could reveal not just that primordial black holes exist, but how they were distributed. Were they evenly scattered like cosmic confetti, or clustered in ways that hint at their formation mechanism? Did they preferentially form during inflation's dramatic expansion, or later during phase transitions when the fundamental forces separated? Each distortion pattern tells a story, and the cosmic microwave background might be preserving narratives from the universe's first trillionth of a second, long before stars or galaxies entered the scene. Of course, the cosmic microwave background isn't giving up its secrets easily. Distinguishing primordial black hole signals from other exotic physics like cosmic strings or early dark energy requires painstaking statistical analysis. But that's what makes this hunt so compelling. Every anomalous cold spot, every unexpected polarization swirl, could be a message from the dawn of time, waiting to be decoded. And if we're right, if these ancient gravitational ghosts really did leave their mark on the universe's first light, it would mean we've been staring at evidence of their existence all along, written across the sky in the faint afterglow of creation. Black holes have always been defined by their relentless gravity and inescapable event horizons, but what if primordial black holes play by different rules? Some theorists propose these ancient objects might not be black holes at all, at least not in the traditional sense. Instead, they could belong to a zoo of hypothetical, exotic compact objects, cosmic oddities that mimic black holes' gravitational pull while dodging their most paradoxical features. Take gravastars, for example. These bizarre constructs would have surfaces made of exotic quantum material instead of event horizons, preventing matter from truly disappearing into a singularity. Or consider dark energy stars, hypothetical objects where the crushing weight of collapsed matter triggers a phase transition, filling their cores with repulsive dark energy that halts total collapse. The appeal of these alternatives lies in how neatly they sidestep black holes' thorniest problems. Singularities, those infinitely dense points at a black hole's core, break physics as we know it, marrying infinite gravity with zero volume in a way that makes equations explode. Exotic compact objects offer an escape hatch. A primordial black hole might conceal not a singularity, but a dense nugget of quark matter or a wrinkle in spacetime leading to another universe. These possibilities aren't just science fiction. They emerge naturally from certain quantum gravity theories, attempting to bridge the gap between general relativity and quantum mechanics. What makes primordial black holes prime candidates for this identity crisis is their formation environment. Born in the quantum chaos of the early universe, they could have stabilized into exotic configurations impossible for stellar black holes. Some models suggest their cores might be made of dark matter particles interacting through unknown forces, creating stable dark cores that look like black holes from afar but lack singularities up close. Others propose they're cosmic knots in spacetime itself, topological defects left over from phase transitions in the infant cosmos. Unlike black holes formed from collapsing stars, which follow predictable mass ranges, primordial variants could have frozen into these exotic states at any size, from microscopic specks to supermassive beasts. The smoking gun would come from subtle differences in how these objects behave. A traditional black hole's event horizon creates a perfect one-way barrier, but exotic alternatives might leave faint traces. Matter colliding with a gravistar's surface could produce unique gravitational wave echoes. Primordial black holes with quantum cores might evaporate differently via Hawking radiation, leaving behind distinct particle signatures. Even their shadows, the dark silhouettes against bright backgrounds, could appear slightly distorted if they lack true event horizons. These minute discrepancies are what next-generation telescopes and gravitational wave detectors are now hunting for, sifting through cosmic noise for hints of physics beyond Einstein. This isn't just academic curiosity, it's a potential paradigm shift. If even a fraction of primordial black holes are exotic compact objects, it would force us to rewrite the cosmic rulebook. Dark matter might not be a cloud of invisible particles, but a swarm of these gravitational imposters. The first supermassive black holes could have grown from exotic seeds rather than stellar remnants. Most profoundly, it would mean the universe has been hiding an entire class of objects that defy our current definitions, operating by quantum rules we've yet to fully grasp. Every unexplained gravitational wave signal, every anomalous microlensing event, becomes a clue in this cosmic detective story, one where the suspects might not be black holes at all, but something far stranger. The search for these exotic possibilities is more than theoretical. Recent gravitational wave data has already flagged a few mergers with peculiar features, echoes that persist milliseconds longer than expected, or mass ratios that don't quite fit stellar models. While none yet confirm exotic compact objects definitively, each outlier fuels the hunt. Upcoming projects like the Einstein telescope will listen for these cosmic whispers with unprecedented sensitivity, potentially catching primordial black holes, or whatever they truly are, in the act of revealing their secrets. What's at stake goes beyond labeling cosmic oddities. If primordial black holes are exotic compact objects, they wouldn't just solve existing puzzles, they'd open new ones. How do quantum effects stabilize such objects over billions of years? Could they be portals to other dimensions or universes? Do their interiors preserve information in ways that resolve the black hole information paradox? Every question underscores how little we truly understand about gravity's most extreme manifestations. The universe may have been craftier than we imagined, weaving relics in its infancy that challenge our definitions while hiding in plain sight. And if we're lucky, the next generation of observatories might finally catch these cosmic chameleons in their true forms. Gamma rays are the universe's most energetic messengers, packets of light so powerful they can outshine entire galaxies in a single flash. When the Fermi Space Telescope began scanning the skies, scientists expected to see gamma rays from known sources like pulsars and supernova, but scattered across its maps are mysterious hotspots with no obvious origin, flickering with energies that defy conventional explanations. One provocative idea ties these cosmic fireworks to the most elusive objects we've discussed: primordial black holes. If these ancient relics collide or evaporate, the violence of those moments could unleash gamma-ray bursts matching Fermi's unexplained signals perfectly. The connection hinges on destruction. When two primordial black holes spiral together, their merger doesn't just send gravitational waves rippling through space, it can also trigger a cataclysmic release of energy. As their event horizons distort and finally merge, surrounding matter gets compressed and heated to unimaginable temperatures, sparking gamma-ray flares detectable across billions of light years. Even more dramatic is the fate of the smallest primordial black holes. Those lighter than 1 billion tons would be approaching the end of their lifespans today, evaporating via Hawking radiation in explosions that concentrate their entire mass into a final, fiery pulse of gamma rays. Picture the energy of an atomic bomb packed into a single photon. That's the scale of violence we're talking about. Fermi's data holds tantalizing clues. In the telescope's all-sky maps, certain gamma-ray sources cluster in ways that don't align with known astrophysical objects. Some appear in regions where dark matter is thought to concentrate, yet they lack the characteristics of typical dark matter particle annihilations. Others flicker with energies that match theoretical predictions for evaporating black holes of brief, intense bursts with no afterglow, as if something vanished in a flash of light. Most intriguing are the diffuse gamma-ray glows lingering near galactic centers, where primordial black holes would naturally accumulate. These could be the collective death throes of countless tiny black holes, their final moments painting the sky with high-energy brushstrokes. Critics counter that gamma rays have many potential sources, from distant quasars to interactions between cosmic rays and gas clouds, but the patterns matter. Primordial black holes wouldn't just produce random gamma rays, they'd leave distinct statistical fingerprints. Mergers would create short, symmetrical bursts, while evaporations would generate a specific spectrum of energies tied to each black hole's mass. Some researchers argue that Fermi has already recorded events matching these profiles, hidden in its vast datasets. The challenge is separating these needles from the cosmic haystack, a task now being tackled by machine learning algorithms sifting through years of observations. The implications stretch far beyond gamma rays. If Fermi's mystery signals do trace back to primordial black holes, it would solve multiple puzzles at once. Not only would it confirm their existence, but it could reveal their distribution across galaxies, their typical masses, and even their role in shaping dark matter halos. Each gamma-ray flash would be like a cosmic census report, telling us how many of these ancient objects lurk in the void. Future telescopes, like the proposed Amigo mission, could take this hunt further by capturing higher-energy gamma rays and pinpointing their origins with unprecedented precision. What makes this detective work so thrilling is its unpredictability. The next gamma-ray burst Fermi detects could be just another collapsing star, or it could be the long-sought proof that the universe is teeming with black holes older than time itself. Every unexplained photon carries that potential, turning the sky into a high-energy treasure map where X might mark the spot for one of cosmology's greatest discoveries. And if we're right, if these gamma rays really are the last cries of evaporating black holes or the birth shrieks of merging ones, then the universe has been signaling us all along in flashes of light only now beginning to be understood. Magnetic fields thread through the cosmos like invisible puppet strings guiding the birth of stars, shaping galaxies, and even influencing the paths of cosmic rays. But here's the puzzle: no one knows exactly how these fields began. They shouldn't exist in the pristine early universe, where everything was too smooth and uniform for magnetic fields to form naturally. Yet today they're everywhere. Could primordial black holes hold the key? Picture these ancient gravitational traps, peppered throughout the infant cosmos, each one stirring the surrounding plasma like a spoon in a turbulent cup of coffee. As charged particles whipped around their event horizons, they might have generated the universe's first magnetic seeds, tiny ripples in space-time's fabric that grew into the vast cosmic fields we see today. The mechanics are as elegant as they are powerful. In the searing heat of the early universe, primordial black holes would have been surrounded by a soup of ionized gas protons and electrons zipping around at nearly the speed of light. Every time one of these charged particles skirted too close to a black hole's gravity, it would have been flung outward, creating electric currents as it moved. Where you have moving charges, you get magnetic fields. even a modest population of primordial black holes could have turned the entire universe into a dynamo, their collective motions amplifying these fledgling fields until they became strong enough to persist for billions of years. What's astonishing is how perfectly this fits with observations. Today's galaxies are wrapped in magnetic fields millions of times stronger than early models can explain, unless something gave them a head start. Primordial black holes provide that kickstart, acting as cosmic anchors around which magnetism could take root. Simulations show that just a handful of these objects per galaxy cluster, each one churning the plasma around it, could have seeded fields strong enough to grow into the intergalactic filaments we detect today. And because magnetism spreads like wildfire in ionized gas, even a few black holes could have magnetized vast swaths of the early universe, but the real magic lies in the timing. Magnetic fields need turbulence to grow, and the early universe was too smooth for conventional theories to work until you add primordial black holes. Their gravity would have created just the right amount of chaos, stirring the cosmic plasma into whirlpools and eddies where magnetic fields could twist and amplify. This solves a chicken and egg problem that's baffled astronomers for decades. How did the first magnetic fields arise without stars or galaxies to create them? The answer might be that black holes came first, their gravitational fingerprints imprinted on the universe's magnetic blueprint long before the first stars flickered to life. The implications ripple across astrophysics. If primordial black holes really did spin up the universe's magnetic fields, it would mean they didn't just shape galaxies, they wired them. Those fields in turn guided the collapse of gas clouds, channeled cosmic rays, and even protected fledgling planetary systems from deadly radiation. Suddenly, these ancient black holes aren't just cosmic oddities, they're the unseen engineers behind one of the universe's most fundamental forces, and the best part, we might already have clues hidden in the magnetic patterns of the cosmic microwave background, subtle twists in polarization that only primordial black holes could have created. Future telescopes like the Square Kilometre Array will map the universe's magnetic fields in unprecedented detail, searching for the telltale signatures of this black hole dynamo. If they find them, it'll be proof that the cosmos was never truly pristine, that from its earliest moments, it was alive with invisible forces, spun into existence by the quiet dance of gravity and plasma around relics we're only now learning to see. The universe's magnetic heartbeat might not belong to stars or galaxies after all, but to the black holes that came before them, silent architects of a force that shapes everything. One of the most puzzling gaps in our cosmic census isn't found among stars or galaxies, it's hiding in the weight class of black holes themselves. Astronomers have long noticed a strange absence of objects between about 2 and 5 times the mass of our Sun, too heavy to be neutron stars, yet suspiciously lightweight for traditional black holes. This cosmic no man's land, dubbed the mass gap, has defied explanation for years. But what if the answer lies not in the death throes of stars, but in the birth pangs of the universe? Primordial black holes, forged in the Big Bang's chaos, could be the missing inhabitants of this gravitational desert, their unusual origins neatly sidestepping the rules that leave stellar collapse with an empty roster. The mass gap's existence reveals a fundamental quirk of stellar physics. When massive stars exhaust their nuclear fuel, their cores collapse under gravity's crush. But nature imposes strict limits on how this plays out. If the collapsing core weighs less than about 2.2 solar masses, it forms a neutron star, a city-sized ball of degenerate matter so dense that a teaspoonful would outweigh Mount Everest. Push past that threshold, and the core keeps collapsing until it forms a black hole. But here's the catch. Models show dying stars rarely leave behind black holes lighter than 5 solar masses. The physics of supernovae essentially skips over the middle ground, creating a conspicuous vacancy in the cosmic lineup, enter primordial black holes, playing by an entirely different rulebook. Unlike their stellar counterparts, these ancient objects didn't form from collapsing stars, they emerged from density fluctuations in the early universe's seething plasma. Without being constrained by stellar evolution strictures, they could have stabilized at any mass, including those elusive gap weights. Picture a universe where countless black holes the size of Jupiter's or small stars pepper the cosmos, each one a relic of quantum irregularities frozen in time. These wouldn't be misfits but natural products of their unique genesis, filling the mass gap simply because they never had to obey stellar physics in the first place. The evidence for this idea comes from an unexpected corner: gravitational wave astronomy. When LIGO detects mergers, most involve black holes comfortably above the mass gap. But a handful of events, like the puzzling GW 190421, featured objects straddling the divide. One participant weighed in at around 2.6 solar masses, too hefty for a neutron star, yet suspiciously light for a conventional black hole. Could this be our first glimpse of a primordial black hole, one that spent billions of years drifting unseen until its fateful collision? The statistical probability of stellar processes producing such an outlier is vanishingly small, but if primordial black holes abound, these oddballs suddenly make perfect sense. What's particularly elegant about this solution is how it ties into larger cosmic mysteries. If primordial black holes populate the mass gap, they wouldn't just be filling a demographic oddity, they'd be contributing to the universe's invisible scaffolding. Their collective gravity could influence the rotation curves of galaxies, subtly alter the timing of pulsar signals, even serve as dark matter candidates. Suddenly, the mass gap isn't an empty stretch of cosmic real estate, but a hidden neighborhood teeming with gravitational relics, each one a time capsule from the universe's first moments. The next generation of gravitational wave detectors, like the Einstein telescope, will be sensitive enough to spot mergers involving even smaller black holes, potentially uncovering a whole population of gap fillers. If they find a statistically significant number of objects in this forbidden range, it won't just solve the mass gap puzzle, it could blow open the case for primordial black holes as a cosmic Swiss Army knife, explaining everything from dark matter's grip on galaxies to the universe's missing baryons. Until then, every gravitational wave signal that lands in this enigmatic zone is a potential Rosetta Stone, waiting to translate the universe's earliest whispers into a language we can finally understand. Fast radio bursts are among the most perplexing signals in the universe. Blasts of radio waves, so powerful they outshine entire galaxies in milliseconds, then vanish without a trace. These cosmic flashes appear randomly across the sky, some repeating mysteriously while others strike once and never return. For years, astronomers have chased theories to explain them, from colliding neutron stars to alien megastructures. But there's another, far stranger possibility lurking in the shadows. What if these brilliant bursts are the death cries of primordial black holes? Picture a pair of these ancient relics, each no wider than a city block but heavier than the sun, locked in a gravitational dance for billions of years. As they spiral closer, their immense gravity distorts spacetime so violently that it generates powerful electromagnetic shocks, a phenomenon called a gravitational dynamo. When they finally merge, that pent-up energy could erupt as a fast radio burst, flooding the cosmos with radio waves before silence returns. Alternatively, the tiniest primordial black holes, those on the verge of evaporating completely via Hawking radiation, might produce FRBs in their death throes. As they shed their final particles, quantum effects near the event horizon could accelerate charged particles to near light speeds, creating a shockwave that ripples outward as an intense radio flash. The timing fits eerily well. Many fast radio bursts originate from incredibly distant galaxies, meaning they occurred when the universe was far younger, precisely when primordial black holes would have been more abundant and active. Some FRBs even show bizarre substructure in their signals, with multiple peaks or strange frequency drifts that could reflect the complex physics of black hole mergers or evaporations. Even more compelling are the rare repeating FRBs, which might trace back to systems where primordial black holes orbit one another in eccentric paths, flaring up periodically as their gravity stirs surrounding plasma into radio-emitting frenzy. But the real smoking gun would come from pairing an FRB with a gravitational wave signal. If telescopes ever catch a fast radio burst coinciding with the space-time ripples of colliding black holes, especially ones too light or too oddly matched to be stellar remnants, it could be the definitive proof that primordial black holes are out there, announcing themselves in bursts of light and ripples of gravity. Projects like the CHIME radio telescope and next-generation gravitational wave detectors are actively searching for these correlated events, sifting through cosmic noise for patterns that might crack the FRB code. What makes this idea so thrilling isn't just solving one mystery, it's the potential to unravel several at once. If primordial black holes produce fast radio bursts, then every FRB becomes a breadcrumb leading us closer to mapping these ancient objects across the cosmos. Suddenly, fleeting radio signals aren't just cosmic curiosities, they're signposts to the invisible architecture of the universe, flashing messages from the darkest corners of space. And if we learn to read them, they might tell us not just where primordial black holes are hiding, but how they've shaped everything from galaxy formation to the very fabric of space-time itself. Axions are one of the most fascinating maybes in modern physics, ghostly particles so light they barely interact with matter, yet collectively they might outweigh all visible stars and galaxies. These hypothetical dark matter candidates have eluded detection for decades, hiding in plain sight as they stream through the cosmos, but what if their secrecy isn't just a quirk of quantum mechanics? Primordial black holes could be pulling the strings, shaping Axions into patterns we're only beginning to recognize. Picture a cosmic dance between the universe's most elusive partners. Axions born from symmetry breaking in the early universe's fundamental forces would have flooded space in unimaginable numbers. Meanwhile, primordial black holes formed from those same chaotic conditions, their gravity warping space-time like invisible boulders in a stream. As Axions pass near these gravitational wells, their behavior could shift dramatically. Some models suggest black holes might act like cosmic catalysts, accelerating action decay into detectable photons, a process that would leave behind faint but distinctive energy signatures. Others propose that Axions could cluster around primordial black holes like moths to a flame, their collective mass amplifying the black hole's gravitational pull in ways that betray both their presence. The implications are staggering. If Axions really do gather around primordial black holes, it would create dense pockets of dark matter regions where these normally diffuse particles concentrate enough to reveal themselves. Experiments like ADAMS, which hunts for Axions converting to microwaves in strong magnetic fields, might suddenly know where to listen. Instead of scanning the cosmic background noise blindly, scientists could focus on areas where primordial black holes are suspected to lurk, tuning their detectors to the specific frequencies action clusters would emit. It's like searching for whispers in a crowded room, only to realize the quietest voices are all huddled around invisible megaphones, but the connection runs deeper than just detection strategies. The interplay between these two dark matter candidates could rewrite the rules of particle astrophysics. Axions are theorized to form Bose-Einstein condensates quantum clouds where particles behave as a single wave. Primordial black holes moving through such condensates would leave gravitational wakes, stirring Axions into patterns that could seed cosmic structure or even imprint detectable ripples in the cosmic microwave background. Some simulations show these interactions might explain why dark matter halos around galaxies have unexpectedly smooth cores, as action waves mediated by black holes redistribute mass over billions of years. The most tantalizing possibility involves quantum anomalies near black hole horizons. As actions skim a primordial black hole's event horizon, extreme gravitational effects could trigger rare quantum transitions, converting them into observable particles. These events would be vanishingly rare, but across trillions of actions and countless black holes, the cumulative effect might create a faint glow across certain wavelengths. Telescopes hunting for this action-born light could be staring at the answer without realizing it, like astronomers before Hubble missing that spiral nebulae were whole galaxies. Critics argue the theory stretches plausibility, requiring precise tuning of action masses and black hole distributions, yet the math holds surprising elegance. If actions exist at the predicted mass scale, around a millionth of an electron volt, their waves would naturally align with the gravitational fields of asteroid mass primordial black holes. It's as if the universe designed these particles to interact, leaving clues in their subtle gravitational choreography. Future experiments like IOXO and upgraded dark matter detectors will test these predictions, hunting for actions where black holes ought to herd them. What makes this synergy so compelling is how it turns competing ideas into collaborators. For years, physicists debated whether dark matter was particle-like actions or macroscopic primordial black holes. But the truth might be both: a cosmic partnership where gravity and quantum physics intertwine to shape the invisible architecture of everything. Every unexplained signal in a dark matter detector, every odd gravitational lensing event, could be a fragment of this larger story. And if we piece it together, we won't just solve one mystery, we'll unlock a hidden dialogue between the universe's smallest particles and its most ancient gravitational monsters. Primordial black holes could be the universe's ultimate time capsules, frozen relics preserving secrets from the very first moments of existence. Unlike stars or galaxies, which evolved over billions of years, these ancient objects formed when the cosmos was less than a second old, locking in the conditions of that chaotic era like insects trapped in amber. Their masses, spins, and even their distribution across the cosmos aren't random quirks but direct imprints of the Big Bang's most violent instance. Imagine holding a primordial black hole in your hand and reading its properties like a cosmic barcode, each digit revealing a piece of the universe's origin story. Take their mass distribution as the first clue. The weight of a primordial black hole depends entirely on the density of the patch of space that birthed it. In the seething plasma of the early universe, quantum fluctuations created tiny overdensities, regions where matter clumped slightly more tightly than its surroundings. If one of these patches collapsed before expansion could smooth it out, it became a black hole, with its mass determined by the size and density of that initial fluctuation. Today, measuring the masses of primordial black holes would give us a snapshot of those quantum ripples, letting us reconstruct the physics of inflation, that explosive growth spurt thought to have shaped the cosmos. A universe that produced mostly asteroid mass black holes, for example, would tell a very different inflationary story than one dominated by black holes as heavy as stars. Then there's spin. Just as a figure skater speeds up by pulling their arms in, primordial black holes could have inherited rotation from the turbulent vortices of the early universe. Their spin rates aren't arbitrary, they're fossils of the angular momentum present in their birth environments. Detect a population of primordial black holes all spinning at similar, unusually high rates, and it might hint at exotic phase transitions or symmetry-breaking events in the cosmos's first microseconds, processes we can't replicate even in our most powerful particle colliders. Even the absence of spin would be revealing, suggesting the early universe was far smoother and more uniform than we've assumed, but the real treasure lies in their arrangement. Unlike black holes born from stars which cluster in galaxies, primordial black holes would mirror the large-scale structure of the infant universe. If they formed during inflation, their distribution should carry faint echoes of the quantum noise stretched across the cosmos, a pattern we could compare to the cosmic microwave background's fluctuations. Find primordial black holes clustered in a specific, statistically improbable way, and it might reveal entirely new forces or fields active during the Big Bang. Some theories even suggest their locations could map out defects in spacetime itself, like cracks in frozen ice, left over from when the fundamental forces of nature first separated. The implications stretch beyond mere curiosity. If primordial black holes preserve details about inflation, they could settle one of cosmology's biggest debates: what powered that exponential expansion? Was it a scalar field, as most models assume, or something more exotic, higher dimensional physics, colliding brains, or even a cascade of phase transitions? Their spins might encode the strength of quantum gravitational effects, offering a rare window into how gravity behaves at energies trillions of times higher than anything achievable on Earth. Even their sheer existence could rewrite the timeline of cosmic events, proving that black holes predated stars, galaxies, and perhaps even atoms. Detecting these time capsules won't be easy, but the tools are coming online. Gravitational wave observatories could soon catch mergers between primordial black holes, their waveforms revealing masses and spins with precision. Microlensing surveys might statistically tease out their distribution, while future telescopes like LISA probe the gravitational hum of the early universe directly. Each observation would be like dusting off an ancient manuscript, its pages filled with equations written in the language of quantum gravity and spacetime's birth pangs. What's thrilling is how little we need to learn everything. Even a handful of confirmed primordial black holes, carefully studied, could reconstruct the universe's first moments with startling clarity. They're not just relics, they're messengers from a time before time, carrying whispers from the edge of existence itself. And if we're right, if these gravitational fossils really do hold the secrets of creation, then the history of the cosmos might be written not in starlight, but in the silent depths of black holes older than light. White holes are the cosmic rebels of theoretical physics, black holes hypothetical opposites, where gravity's grip reverses into an unstoppable outburst. Picture a singularity that refuses to swallow matter, instead violently expelling everything that comes near it, like a cosmic fire hose blasting energy into the void. While no white hole has ever been observed, their possibility emerges straight from Einstein's equations, hiding in the same math that predicts black holes. And here's where primordial black holes twist the plot. If these ancient gravitational traps survive long enough, quantum mechanics suggests they might not just fade away, they could flip inside out, transforming into white holes in a process as bizarre as it is beautiful. The transformation hinges on a quantum gamble. As a primordial black hole evaporates via Hawking radiation, shedding mass until it approaches microscopic scales, spacetime itself becomes unstable at its event horizon. Under these extreme conditions, some theories propose the black hole could tunnel through the fabric of reality, emerging as its opposite, a white hole spewing out the trapped remains of everything it ever consumed. It wouldn't be a rebirth in the traditional sense, but a cosmic reset, where the black hole's crushing gravity gives way to an explosive repulsion. The energy released wouldn't just be random radiation, it might carry echoes of the matter and energy swallowed over billions of years, like a time capsule rupturing open. What makes this idea so radical is the timeline. Stellar black holes take longer to evaporate than the current age of the universe, but the tiniest primordial black holes, those lighter than a small mountain, could be reaching this critical threshold right now. If even a fraction of them undergo this transformation, the cosmos might be peppered with fleeting white hole explosions, their gamma-ray signatures blinking in the darkness before vanishing forever. Telescopes hunting for unexplained high-energy bursts could already be detecting these events without realizing it, mistaking them for supernova or neutron star collisions. The implications cascade across cosmology. If primordial black holes can morph into white holes, they might solve the black hole information paradox, a long-standing puzzle about whether matter swallowed by black holes is truly lost forever. White holes would offer an escape route, preserving information by eventually ejecting it back into the universe, scrambled but not destroyed. Even more mind-bending is the possibility that some white holes could outlive their black hole predecessors, lingering as persistent fountains of energy in otherwise empty space. Galaxies might even form around these cosmic geysers, their outbursts seeding star formation in ways we've never imagined, yet the theory isn't without its skeptics. White holes violate the second law of thermodynamics by seemingly decreasing entropy, and no known process in nature naturally creates them. Only the quantum resurrection of dying black holes offers a plausible path. Some physicists argue that the transformation would take longer than the age of the universe, rendering white holes permanently hypothetical. Others suggest that even if they form, their outbursts would collapse back into black holes almost instantly, trapped by their own intense gravity. The debate rages, but that's the beauty of primordial black holes. They force us to confront the wildest edges of physics, where relativity and quantum mechanics clash in a shower of paradoxes. The search for evidence is already underway. Astronomers are re-examining anomalous gamma-ray bursts for hints of white hole signatures, sudden, symmetric energy releases with no afterglow. Gravitational wave detectors might one day catch the space-time ripples of a black hole's final quantum leap, a distinctive chirp as it flips inside out. And if we're spectacularly lucky, a primordial black hole nearing the end of its life might be close enough for us to witness its transformation in real time, offering front-row seats to a cosmic metamorphosis older than the stars themselves. Whether white holes exist or not, the mere possibility reshapes how we view primordial black holes. They're not just relics, they're potential time bombs, ticking away until the moment they rewrite their own destinies. And if that moment comes, the universe might reveal a side of itself we've never seen, not just a graveyard of collapsed matter, but a rebirth of energy, where even the darkest corners of space hold the seeds of resurrection. The hierarchy problem is one of physics' most frustrating mysteries. Why is gravity so unbelievably weak compared to the other fundamental forces? Picture this: a tiny magnet can lift a paperclip, effortlessly overcoming Earth's entire gravitational pull. At the quantum level, the disparity becomes even more absurd. Gravity is a staggering 10 to the 39th times weaker than electromagnetism. This isn't just a curiosity, it's a glaring inconsistency in our understanding of reality. But hidden in the extreme physics of primordial black holes, there might be a path to solving this cosmic riddle. These ancient gravitational anomalies operate where quantum mechanics and general relativity collide, precisely the regime where the hierarchy problem festers. Unlike ordinary black holes, primordial ones could span masses from subatomic to supermassive, giving us a sliding scale to study how gravity behaves across different scales. Their smallest versions, lighter than a speck of dust yet denser than a star, would be dominated by quantum gravitational effects. If we could observe how these microscopic black holes interact with matter, it might reveal why gravity seems to leak out of our three-dimensional space into hidden dimensions, a leading explanation for its apparent weakness. Some theories suggest extra spatial dimensions could dilute gravity's strength, and primordial black holes' evaporation patterns or merger signatures might carry fingerprints of these hidden realms. What makes this approach so powerful is its directness. Particle accelerators like the Large Hadron Collider smash protons together at near light speeds, trying to create conditions where gravity might finally match other forces' intensity. But even these colossal machines can't reach the necessary energies. It would take a collider the size of our galaxy. Primordial black holes, though, naturally achieved these extremes in the early universe's chaotic birth. Their existence would mean nature already performed the experiment for us, leaving behind gravitational relics we can study. By analyzing their Hawking radiation or gravitational wave emissions, we might spot anomalies that point to new symmetries between forces, perhaps even evidence that gravity wasn't always the feeble outlier it appears to be today. The implications ripple across theoretical physics. If primordial black holes decay faster or slower than predicted, it could hint at undiscovered particles modifying gravity at small scales. Their spin rates might encode clues about supersymmetry, a theoretical framework that pairs every known particle with a heavier, shadow partner to balance the forces. Even their distribution in space could test string theory's predictions about how the universe's fundamental strings curled up during inflation. Every deviation from Einstein's classical predictions would be a breadcrumb leading toward a grand unified theory, one where gravity finally takes its place alongside electromagnetism and nuclear forces as an equal player. Critics argue that primordial black holes are too speculative to pin such hopes on, but that's precisely what makes them so valuable. They force us to confront the limits of our knowledge. Whether they exist or not, the mathematical hunt for them has already spurred new ideas about quantum gravity, extra dimensions, and the nature of spacetime itself. And if we do find them, their extreme physics might finally answer why we live in a universe where a planet's gravity can lose a tug of war with a child's refrigerator magnet, a mystery as old as physics itself, written in the language of black holes older than time. The idea that our universe might be just one bubble in an infinite cosmic foam has long hovered at the edge of physics, a tantalizing possibility that's impossible to prove, yet refuses to disappear. But what if primordial black holes are the key to finally testing this radical vision? Some multiverse theories propose that when parallel universes brush against our own in higher dimensional space, the gravitational shockwaves could collapse pockets of reality into ultra-dense knots, forming primordial black holes like cosmic fingerprints at the boundaries between worlds. These wouldn't be ordinary black holes with stellar origins, but literal bruises on the fabric of our universe, marking where another reality briefly pressed too close. Think of space as a vast, multidimensional sheet of rubber. When other universe bubbles expand nearby, their pressure might create dimples in our spacetime regions so warped they pinch off into black holes. The math behind this is mind-bending, but the implications are startlingly concrete. If we could study a population of primordial black holes and find their masses clustered in specific, unexpected ranges, or their spins aligned in improbable patterns, it might betray their origins as collision scars from other realities. Unlike black holes born from dying stars, these multiverse artifacts would carry no trace of stellar nucleosynthesis, no heavy elements, no accretion disks, just pure gravitational signatures shaped by physics beyond our cosmic horizon. The most provocative clue would come from their distribution. In an infinite multiverse, collisions wouldn't be random. They'd follow statistical patterns tied to the geometry of higher dimensions. Primordial black holes formed this way might cluster along invisible fault lines in space, tracing out the contours where parallel universes most often graze ours. Future sky surveys mapping black hole positions could reveal these ghostly architectures not just random scatterings, but intricate networks of gravitational hotspots hinting at structures far larger than our observable universe. Of course, skepticism is warranted. The multiverse remains untestable by conventional means, and attributing any unexplained phenomenon to other universes risks becoming a modern-day cosmic ether, a catch-all explanation that explains nothing. But here's what makes primordial black holes different. They offer a rare, potentially measurable link between speculative theory and observable reality. While we can't directly probe other universes, we might detect their gravitational echoes in the properties of these ancient black holes. Their masses could encode the energy scales at which universes interact. Their spins might preserve the angle at which realities collided. Even their evaporation rates could carry subtle anomalies, betraying quantum leakage from adjacent dimensions. The stakes couldn't be higher. If primordial black holes do bear multiverse signatures, it would mean every detection isn't just studying our cosmic history, it's archaeology of the metacosmos, digging into layers of reality we once thought forever inaccessible. And if they don't, their absence would force us to reconsider whether the multiverse leaves any imprint at all, narrowing down which theories remain plausible. Either way, these gravitational relics become more than cosmic oddities, they're messengers from the edge of everything, carrying whispers of whether we live in a solitary universe or one of countless bubbles in a froth of realities beyond imagining. Black holes don't just bend space-time, they might shred the very rules of reality as we know them. At the heart of this crisis lies the black hole information paradox, a puzzle so profound it's divided physicists for decades. Quantum mechanics insists that information, the fundamental details of every particle's state, can never truly vanish, yet black holes, with their event horizons and crushing singularities, seem to erase it permanently. This isn't just a philosophical quibble, it's a glaring contradiction between our two most successful theories of the universe. But primordial black holes, forged in the quantum chaos of the Big Bang, could finally break the deadlock, offering a cosmic lab to test solutions like the holographic principle or firewalls, ideas that once seemed untouchable by experiment. Consider the holographic principle, one of the boldest attempts to reconcile this paradox. It suggests that all the information swallowed by a black hole isn't lost inside but smeared across its event horizon like a cosmic fingerprint, encoded in two-dimensional quantum bits. For stellar black holes, this is nearly impossible to verify. Their horizons are too turbulent, their environments too noisy, but primordial black holes, especially those small enough to evaporate within cosmic timescales, could put this theory to the test. As they decay via Hawking radiation, their final moments might release subtle imprints of the information they once consumed, like a scrambled radio signal finally clearing into coherence. If we could catch these evaporation signatures, they'd reveal whether information truly escapes or remains trapped forever. Then there's the firewall hypothesis, a radical idea suggesting that event horizons aren't the smooth gateways Einstein predicted but seething walls of high-energy particles, a last-ditch mechanism to preserve information by burning it into outgoing radiation. For massive black holes, firewalls are theoretical specters, but primordial black holes could make them tangible. Their smaller size means quantum effects dominate their behavior, amplifying any firewall-like phenomena to detectable levels. Imagine a primordial black hole's evaporation flaring with unexpected high-energy particles, a potential smoking gun for this controversial solution. Even their mergers, detectable by gravitational wave observatories, might carry anomalies in their waveforms, hints that information isn't vanishing quietly, but fighting its way out through space-time seams. What sets primordial black holes apart is their pristine origin. Unlike stellar black holes, which form from the messy collapse of stars laden with heavy elements and magnetic fields, these ancient relics condense directly from the universe's smooth, quantum-scaled infancy. That purity means they could preserve quantum information in ways their stellar counterparts can't, like a flawless diamond locking in light undistorted. Some theories suggest their cores might not even host singularities but exotic quantum states, Planck stars or wormholes, where information is stored, not destroyed. If so, their evaporation or collisions wouldn't be endpoints but transformations, with data re-emerging in new configurations we're only beginning to model. The stakes transcend academic debate. Resolving the information paradox wouldn't just tidy up physics equations, it would redefine our understanding of causality, entropy, and the nature of reality itself. If primordial black holes prove information can escape, it implies the universe has a built-in cosmic ledger, a way to balance its quantum books no matter how extreme the conditions. Conversely, if they confirm information's destruction, it forces us to rewrite quantum mechanics or accept that black holes are truly existential exceptions to nature's rules. Upcoming experiments are poised to turn speculation into evidence. Next-generation gravitational wave detectors could spot mergers with telltale information preserving echoes. High-energy telescopes might catch the distinctive photon spectra of evaporating black holes, their energy distributions betraying whether data leaks out subtly. Even quantum computers, simulating black hole dynamics in controlled environments, could uncover how information navigates these gravitational labyrinths. This isn't just about black holes, it's about whether the universe plays fair with its own rules. Primordial black holes, as relics from creation's first moments, hold the receipts for cosmic transactions we've long assumed were lost. Their silence or their whispers could finally answer whether information, like energy, is truly conserved, or whether black holes are the universe's ultimate shredders, leaving us with a puzzle that defies the very foundations of physics. High-energy cosmic rays streak through the universe like bullets fired from cosmic accelerators. We don't yet understand particles packing enough punch to rival a fastball thrown at nearly the speed of light. While most originate from supernova or active galactic nuclei, a stubborn fraction defy explanation, arriving with energies so extreme they shouldn't exist under known physics. This is where primordial black holes enter the scene, offering a tantalizing solution. Imagine one of these ancient relics, smaller than an atom yet heavier than Everest, finally succumbing to quantum evaporation after billions of years. In its last milliseconds, it wouldn't fade quietly, it would erupt, converting its entire mass into a burst of high-energy particles blasting outward in all directions. Some of those particles could be racing through space right now, eventually slamming into Earth's atmosphere as cosmic rays with unmistakable fingerprints. Detecting these signals turns our planet into the ultimate particle detector. When ultra-high-energy cosmic rays hit the upper atmosphere, they trigger cascades of secondary particles, air showers that spread over kilometers like invisible fireworks. Ground-based observatories like the Pierre Auger array meticulously map these showers, reconstructing the original particle's energy and type. Most match known astrophysical sources, but a rare few carry signatures that make physicists pause. Anomalous spikes in gamma rays, unexpected ratios of positrons to electrons, or particles clustered around specific energy thresholds could all hint at primordial black holes dissolving in distant corners of the cosmos. The key lies in the details. Evaporating black holes should produce particle spectra distinct from standard astrophysical processes, with telltale bumps or cutoffs tied to quantum gravitational effects. Collisions offer another explosive avenue. If two primordial black holes merge in deep space, the surrounding plasma could become a particle accelerator of cosmic proportions. Magnetic fields near the event horizon might whip charged particles to energies dwarfing anything achievable in human-made colliders, launching them across the universe as cosmic rays. These wouldn't just be random high-energy particles that arrive in correlated bursts, their directions tracing back to regions where dark matter and potentially PBHs cluster. Future observatories like the Cherenkov Telescope Array could spot these patterns, effectively using the sky as a canvas where primordial black holes paint their presence in streaks of rare, ultra-energetic particles. The real breakthrough would come from combining cosmic ray data with other cosmic messengers, A high-energy particle coinciding with a gravitational wave signal or an unexplained gamma-ray flash would be like catching a criminal on multiple surveillance cameras, irrefutable proof linking the event to a primordial black hole. Even more compelling would be detecting particles that shouldn't exist in standard models, like stable magnetic monopoles or certain supersymmetric particles, which some theories predict could be forged in the extreme conditions near evaporating PBHs. These wouldn't just confirm primordial black holes, they'd open doors to new physics, revealing particles or forces that have eluded our most powerful colliders. Critics argue that cosmic rays are too messy a signal, too easily mimicked by other exotic astrophysics, but that's precisely why next-generation detectors are game changers. By analyzing air showers with nanometer precision and cross-referencing them with neutrino and gravitational wave data, scientists can filter out false positives. The strategy mirrors forensic science, isolating rare patterns from background noise until only the truth remains, and if that truth points to primordial black holes, it would mean we've been standing under a cosmic waterfall of their debris for centuries, only now learning how to read the messages hidden in the deluge. What's at stake isn't just another entry in the catalog of cosmic objects, it's a paradigm shift in how we hunt for the invisible. Traditional astronomy relies on light, but primordial black holes demand we become fluent in the language of particles and gravity. Every anomalous cosmic ray could be a telegram from the early universe, sent via a delivery mechanism older than stars themselves, and as our detectors grow more sophisticated, we might find that the answers to cosmology's biggest puzzles have been raining down on us all along, waiting for the right tools to catch them. Imagine a universe where primordial black holes weren't rare cosmic oddities, but as common as stars. Galaxies would be pockmarked with gravitational mines, their delicate spiral arms shredded by countless invisible disruptors. Planetary systems forming in such a chaotic environment would face constant peril. One stray encounter with a wandering black hole the size of a mountain, and an entire planet could be ripped apart without warning. This isn't just speculative fiction, it's a window into why our universe seems to have carefully limited the number of these ancient gravitational relics. The anthropic principle, a controversial but compelling line of reasoning, suggests that primordial black holes might be scarce precisely because their overabundance would make life impossible. The logic cuts straight to the heart of cosmic fine-tuning. For life to emerge, the universe needed stable galaxies with predictable orbits, planets shielded from constant gravitational bombardment, and enough time for complex chemistry to unfold. Too many primordial black holes would have thrown this delicate balance into chaos. Their gravity would have disrupted the early universe's smooth distribution of matter, preventing the formation of the vast cosmic webs that cradle galaxies. Even a modest excess would have turned the cosmos into a minefield, with black holes zipping through interstellar space at hundreds of kilometers per second, silent wrecking balls, capable of vaporizing entire solar systems in passing. The fact that we don't observe this carnage hints that nature, whether by accident or deeper design, kept their numbers in check. Digging deeper reveals an even more fascinating possibility. The scarcity of primordial black holes might not be random, but a consequence of fundamental physics. Inflation, the universe's explosive early expansion, could have smoothed out density fluctuations just enough to prevent excessive black hole formation. Alternatively, quantum effects at the smallest scales might have set a natural limit on how many regions of space could collapse into these gravitational traps. Some theories even suggest that dark matter, long thought to be a separate entity, could actually be the leftover primordial black holes that didn't disrupt cosmic evolution, their mass carefully distributed to avoid catastrophic consequences. This isn't just about black holes, it's about the universe's remarkable ability to regulate itself. The same forces that allowed galaxies to form, stars to ignite, and planets to coalesce may have also quietly suppressed the most dangerous relics of the Big Bang. Whether by sheer luck or some yet unknown law of nature, primordial black holes exist in a Goldilocks zone, numerous enough to potentially explain dark matter or seed supermassive black holes, yet sparse enough to let life arise undisturbed. Their rarity might be the universe's silent compromise between chaos and order, a hidden rule written into the fabric of spacetime itself. The implications ripple beyond astrophysics into philosophy. If the abundance of primordial black holes is fine-tuned for life, does that suggest our universe is uniquely suited for consciousness, or merely one of countless variations where conditions happen to align? Future discoveries could tip the scales. Finding even a small population of these objects would illuminate how finely the dials of reality were set, offering clues to whether our existence is a cosmic accident or the product of deeper principles we've yet to uncover. Either way, primordial black holes aren't just celestial curiosities, they're silent witnesses to the universe's most profound balancing act, one that allowed both gravity's monsters and living creatures to share the same cosmic stage. At the heart of every black hole lies the ultimate cosmic mystery, the singularity, a point where gravity becomes infinite and spacetime itself shatters into mathematical chaos. For decades, physicists have treated singularities as unavoidable predictions of Einstein's equations, the grim fate awaiting anything crossing a black hole's event horizon. But primordial black holes, forged in the quantum fires of the Big Bang, might rewrite this story entirely. Unlike their stellar-born cousins, these ancient objects could defy the classical rules, offering a glimpse beyond the singularity's veil into realms where quantum gravity takes control. Picture spacetime not as a smooth fabric, but as a seething quantum foam at the smallest scales, a turbulent sea where gravity and uncertainty intertwine. In this frenzied environment, the infinite density of a classical singularity becomes impossible, like trying to balance an entire mountain on the tip of a needle. Quantum effects would intervene long before matter reached that extreme state, potentially replacing the singularity with something far stranger, a dense, fuzzy core where the very concepts of inside and outside blur. Some theories suggest these cores could be Planck stars, exotic objects with the mass of a black hole, compressed into a volume trillions of times smaller than an atom, yet still finite. Others propose wormholes, quantum bridges threading through hidden dimensions, or even bubbles of new universes budding off from our own. What makes primordial black holes ideal for testing these radical ideas is their purity. Stellar black holes form from the messy collapse of stars, their interiors polluted by heavy elements and violent magnetic fields, but primordial black holes condense directly from the universe's raw energy, their cores untouched by stellar nucleosynthesis. If quantum gravity leaves fingerprints anywhere, it's here in objects that have spent billions of years evolving in isolation, free from astrophysical noise. Their evaporation patterns could reveal anomalies in Hawking radiation, subtle deviations hinting at structures more complex than a singularity. Even their mergers might produce gravitational wave echoes, faint ripples betraying the presence of a quantum surface just beneath the event horizon. The stakes couldn't be higher. If primordial black holes lack true singularities, it would mean spacetime never fully breaks down, it transitions. The crushing weight of a black hole's core wouldn't mark the end of physics, but the beginning of something new, a phase change akin to water freezing into ice. This shift in perspective could resolve the black hole information paradox, suggesting that what falls in isn't lost but transformed, encoded in quantum fluctuations at the horizon. It might even hint at a deeper unity between gravity and quantum mechanics, showing how spacetime emerges from more fundamental building blocks we've yet to discover. Critics argue that without direct observational evidence, these ideas remain speculative, but the universe might already be sending us clues. The gravitational waves from colliding black holes sometimes carry unexpected features, extra oscillations, or resonant frequencies that don't fit classical models. Could these be echoes of quantum structures rebounding inside? Future observatories like the Einstein telescope will listen for these whispers with unprecedented precision, potentially catching primordial black holes in the act of revealing their hidden interiors. Whether singularities exist or not, primordial black holes force us to confront the limits of our knowledge. They're not just cosmic relics, they're portals to the edge of physics, where the rules we take for granted dissolve into possibilities we've barely begun to imagine. And if we're right, if these ancient objects really do guard the gates to quantum gravity's realm, then the universe's darkest corners might be its most illuminating. The hunt for primordial black holes is about to enter its most exciting phase, armed with telescopes and detectors so advanced, they could turn what was once theoretical speculation into observational reality. Leading the charge is LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s. Unlike ground-based gravitational wave observatories, LISA trio of satellites will orbit the Sun in perfect formation, forming a gravitational wave detector with arms millions of kilometers long. This colossal scale lets it tune into frequencies impossible to catch on Earth, the telltale ripples from merging primordial black holes in the early universe. Imagine listening for the faint echoes of collisions that occurred before the first stars ignited, when space was so dense that black holes routinely paired off in cosmic dances. If primordial black holes exist in the elusive intermediate mass range between 100 and 1,000,000 solar masses, LISA sensitivity could catch their mergers with startling clarity, their waveforms spelling out masses and spins that betray a non-stellar origin. Meanwhile, the James Webb Space Telescope is rewriting the rules of infrared astronomy, and it might just spot primordial black holes hiding in plain sight. While these ancient objects don't emit light, their gravity bends and magnifies the glow of background galaxies through gravitational lensing. JWST unprecedented infrared vision can detect distortions too subtle for earlier telescopes, potentially revealing black holes drifting alone in intergalactic space. Even more tantalizing are the unexplained infrared glows around some of the universe's first galaxies. If primordial black holes seeded these early structures, their voracious feeding would have heated surrounding dust, leaving behind thermal fingerprints JWST instruments are uniquely equipped to trace. A single anomalous heat signature in the distant cosmos could be the smoking gun that links supermassive black holes to their primordial ancestors. Then there's the Vera Rubin Observatory, poised to revolutionize time-domain astronomy when it begins its 10-year legacy survey of space and time. With a camera the size of a small car and the ability to scan the entire visible sky every few nights, Rubin will catch fleeting cosmic events most telescopes would miss. For primordial black holes, this means two critical opportunities. First, microlensing those momentary brightenings when a black hole passes in front of a distant star. Rubin's sheer volume of observations will catch thousands of lensing events, and hidden in that data could be the distinctive curves of asteroid mass black holes, too small and fast for previous surveys to spot. Second, Rubin might catch the rare instances when a primordial black hole plows through a gas cloud or star cluster, triggering flares as surrounding matter gets compressed and heated. These transient phenomena, once dismissed as noise, could turn out to be the universe's way of highlighting invisible gravitational traps, but the future doesn't stop there. The Einstein telescope, a next-generation gravitational wave detector buried deep underground, will be sensitive enough to hear mergers involving black holes lighter than our Sun, in precisely the mass range where primordial black holes could solve the dark matter puzzle. The Square Kilometre Array, a radio telescope spanning continents, could detect the whispers of evaporating black holes in their final, explosive moments. Even the humble neutrino detector, buried under Antarctic ice, might catch particles flung from primordial black hole collisions, their energies betraying origins no stellar process could replicate. What makes this era so transformative isn't just the technology, it's the convergence of multiple lines of evidence. A gravitational wave signal from LISA, paired with an infrared anomaly from JWST and a microlensing event from Rubin, would form an irrefutable chain of proof. For the first time in history, we're not just searching for primordial black holes, we're building the tools to triangulate their existence from every angle. And if they're out there, these ancient gravitational ghosts won't stay hidden much longer. The universe wrote their story 13 billion years ago. Now at last we're learning how to read it. Primordial black holes might stitch together cosmic mysteries with elegant solutions, but not everyone is convinced they're the missing thread. For every tantalizing clue, an unexplained gravitational wave signal, a flicker of microlensing, there are alternative explanations that don't require rewriting the universe's first chapter. Dark matter could still be an undiscovered particle, like WIMP or Axions, lurking just beyond our detector's current reach, those oddly massive black holes in the early universe. Perhaps they grew faster than we thought, fueled by freakish stellar conditions or dense gas clouds we've yet to model accurately. Even the cosmic microwave background's quirks might trace back to exotic physics during inflation, not the gravitational fingerprints of ancient black holes. The heart of the skepticism lies in Occam's razor, the principle that the simplest explanation is often the best. Primordial black holes demand a cosmic coincidence, that the right density fluctuations existed in the early universe to form them, but not so many that they'd have disrupted the cosmos beyond recognition. Critics argue that invoking PBHs to explain dark matter, galaxy formation, and more risks turning them into a theory of everything, patching over gaps in our knowledge rather than filling them with evidence. It's a charge that stings because it's not entirely wrong. Science thrives when ideas face relentless scrutiny, and PBHs are no exception, yet the debate is far from one-sided. What sets primordial black holes apart isn't just their explanatory power, but their testability. Unlike some dark matter candidates that remain frustratingly invisible, PBHs leave gravitational footprints we can actively hunt for. When LIGO detects a merger between two black holes too heavy to form from stars, or when a telescope catches a star brightening in ways no known object can explain, these aren't just anomalies, they're potential breakthroughs. The controversy isn't a weakness, it's a catalyst driving better observations, sharper theories, and ultimately, a clearer picture of reality. The tension between skepticism and discovery is how science progresses. Every revolutionary idea, from plate tectonics to the Big Bang, itself faced fierce resistance before the evidence became undeniable. Primordial black holes are no different. Whether they ultimately triumph or fade into cosmic history, their real value lies in pushing us to ask better questions, build better tools, and stay open to the universe's endless capacity to surprise. After all, the most exciting breakthroughs don't come from consensus, they emerge from the friction between what we think we know and what the cosmos is quietly trying to tell us. Primordial black holes aren't just relics of the past, they might be the unseen architects of the universe's ultimate destiny. If these ancient gravitational traps make up even a fraction of dark matter, their quiet influence could steer the cosmos toward a future far stranger than we've imagined. Picture a universe where black holes aren't just endpoints but active players in its grand finale, their mergers and evaporations rewriting the rules of cosmic decay. As galaxies drift apart in the accelerating expansion of space, these primordial remnants could become the last gravitational anchors in an increasingly dark and empty void, their slow dances determining whether the cosmos fades into icy stillness or erupts in unexpected rebirth. Consider heat death, the traditional view of the universe's end, where all energy disperses into a lifeless, uniform haze. Primordial black holes might accelerate this process in eerie ways. As they merge over unimaginable timescales, their collisions would pump gravitational waves into the fabric of space-time, energy that gradually redshifts into nothingness, sapping the universe's usable heat. Tiny black holes nearing evaporation would add another twist, their final bursts of Hawking radiation briefly lighting up the darkness like dying embers before vanishing entirely. In this scenario, the last flickers of activity in a cold, expanding cosmos wouldn't come from stars or galaxies, but from these ancient gravitational time bombs finally exhausting themselves. But there's a wilder possibility. If primordial black holes harbor secrets beyond Einstein's equations, quantum bridges to other dimensions, or exotic matter cores, their decay might not be an endpoint, but a transition. Some theories suggest their evaporation could spawn new universes in a fractal chain of cosmic rebirth, like seeds scattered from a dying plant. Imagine a black hole's final moments not as a whisper, but as a big bang in miniature, birthing an entirely new spacetime bubble with its own laws of physics. In this mind-bending vision, our universe's death might sow the seeds for countless others, with primordial black holes acting as cosmic midwives at the edge of existence. The most dramatic twist lies in their potential to alter dark energy's grip on the cosmos. If black holes store vacuum energy in their singularities, or if their evaporation releases latent energy tied to quantum fields, they could subtly shift the balance between expansion and collapse. A universe teeming with evaporating primordial black holes might see its acceleration slow or even reverse as gravitational influences reassert themselves, turning the tide against dark energy's dominion. It's a long shot, but the mere possibility forces us to rethink the universe's fate as something more dynamic than a one-way slide into entropy. Yet the ultimate irony is this: if primordial black holes dominate dark matter, they might ensure their own obsolescence. As the cosmos expands and matter thins, their merger rates would plummet, leaving isolated black holes drifting eternally in the void. Their once formative influence would fade, reduced to gravitational footnotes in a narrative stretching trillions of years into the future. The same objects that could have jump-started galaxy formation and shaped dark matter's structure might end as spectral sentinels, watching over a universe too vast and cold to remember their beginnings. What's startling is how much hinges on their existence. Without primordial black holes, the far future looks like a predictable march toward dissipation. With them, it becomes a canvas for quantum uncertainty and gravitational surprises, a reminder that the universe's first moments might hold sway over its last. Whether as catalysts of heat death or agents of cosmic renewal, these ancient relics could prove that the story of everything isn't just about where we've been, but where we're ultimately headed. And if we're lucky enough to find them, their whispers might carry not just echoes of the Big Bang, but prophecies of the end. Primordial black holes aren't just cosmic oddities, they're keys to unlocking some of the universe's most stubborn mysteries. Imagine rewriting the story of dark matter, not with hypothetical particles, but with ancient gravitational traps hiding in plain sight. Picture cracking open the secrets of the Big Bang itself by studying objects forged in its first chaotic moments. These aren't just thought experiments, they're real possibilities that could reshape our understanding of everything from galaxy formation to the fate of the cosmos. The beauty of primordial black holes lies in their versatility. They're not one-trick wonders, they're cosmic multitaskers. If they exist, they could be the invisible glue holding galaxies together, the seeds sprouting supermassive black holes, even the reason our universe looks the way it does today. And let's not forget their role as time capsules, each one a frozen snapshot of the universe's fiery infancy. preserving quantum fluctuations and gravitational ripples from a time before atoms, before light, before anything we'd recognize as the cosmos we know. But here's what's truly thrilling: we're not just waiting for answers, we're actively hunting for them. Right now, gravitational wave detectors are listening for the whispers of collisions older than stars. Telescopes are scanning the skies for the telltale twinkle of microlensing events that betray these invisible wanderers. Even particle detectors buried deep underground might catch the faint echoes of a primordial black hole's quantum evaporation. Every unexplained signal, every anomalous burst of radiation, could be the clue that cracks this case wide open. What makes this search so urgent is how much it challenges our assumptions. For decades, we've operated under certain rules: black holes form from dying stars, dark matter must be some exotic particle. The early universe was too smooth for structures like black holes to exist. Primordial black holes turn all that on its head. They force us to ask, what if we've been missing something fundamental? What if the answers to our biggest questions have been hiding not in the complex physics of hypothetical particles, but in the elegant brutality of gravity itself? The implications stretch beyond astrophysics textbooks. If we confirm primordial black holes, it would be like finding a hidden chapter in the universe's autobiography, one that changes how we interpret every other page. Suddenly, dark matter isn't an abstract concept, but tangible objects we might one day map. The cosmic microwave background becomes not just a baby picture of the universe, but a treasure map to its gravitational fossils. Even the search for extraterrestrial life gets a new dimension. Could these ancient black holes influence the development of habitable planets in ways we've never considered? Yet for all their potential, primordial black holes remain elusive. They're the ultimate cosmic hide-and-seek champions, revealing themselves only through subtle gravitational nudges and fleeting electromagnetic whispers. That's what makes this hunt so exhilarating. We're chasing shadows, but shadows that could rewrite the rules, and with every new tool we build, from space-based interferometers to AI-powered sky surveys, we're closing the net tighter. So here we stand at a remarkable crossroads in cosmic exploration. The pieces are all in place, the theories are robust, the technology is advancing, and the questions have never been sharper. Whether primordial black holes turn out to be everywhere or nowhere, the search itself is expanding our understanding of what's possible. They remind us that the universe specializes in surprises, hiding its greatest secrets in the most unexpected places. And if history is any guide, the next big breakthrough isn't just coming, it's lurking just beyond our current view, waiting for the right moment to step into the light.